In today's lesson, we are going to be looking at different number sets. So this is going to be a little bit different from some of our previous lessons. This is going to be a little bit more focused on some of more of the theory, I guess you could say, and concepts rather than calculations. So what are number sets? Well, with all the numbers that we have looked at, there are different sets of numbers, basically different groupings of numbers based on their characteristics. And all the numbers that we have been using, all the numbers that you see, all the numbers that you know right now, belong to a large overall set called real numbers. So this is any number that we can think of, any number that we've worked with in the past has been a real number. And real numbers can be broken down into different subsets with different characteristics. So we're going to start off with the most basic. The most basic set, or the simplest set of or subset of real numbers, are natural numbers. And natural numbers are whole positive numbers, not including zero. And they're also called counting numbers, as you can imagine. It's how we count things. 1, 2, 3, 4, 5, 6, 7, and so on. Right? So whole positive numbers, not including zero, are considered what we call counting numbers. Now, the next set, and basically the way this works, it's kind of like in like shells. So this is the smallest shell, or if you think of those nesting dolls that you see where it's a small doll inside of a larger doll, inside of a larger doll, that type of thing. Natural numbers are at the very center. So natural numbers are at the center, and then the next subset are whole numbers. So whole numbers include natural or counting numbers, and whole numbers are whole positive numbers, but now we can include zero. So whole numbers are all your counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, plus zero. So zero is now included. So you can think of a ruler going from zero, counting the centimeters, specifically the centimeters, and we'll talk about why. 0, 1, 2, 3, 4, 5. Think of a lock, 1, 0, 1, 2, 3, 4, 5, and so on. Think of an air pressure cuff, 0, 1, 2, 3, 4, 5, and so on. So whole numbers are all the positive numbers, or positive whole numbers, and zero. The next subset, so the larger shell, so basically it includes all the other numbers, but now we're going to add something new. And the next subset is integers. We've talked about integers already in our first lesson. We've looked at integers, we've worked with them, right? Integers are positive and negative whole numbers, including zero, right? So now we're not just looking at the positive side, we are now also looking at the negative side. So we can think of things such as temperature, altitude, or sea level or depth, right? Go positive above sea level, below sea level. You can think of stocks rising in value, losing value, positive and negative. You might have a zero value in there if it's not worth anything. Right, so again, integers are positive and negative whole numbers, including zero. Rational numbers is one step further. Rational numbers, again, include your whole numbers, your counting, or your natural numbers, your whole numbers, your integers. And rationals also include now fractions and decimals. So any type of fraction, basic fraction, right? Proper, improper, any type of fraction is considered a rational number, and certain decimals. If the decimal comes from a fraction, chances are it is a rational number. Now, one key thing with the decimals, though, is that there are two key characteristics that we've highlighted here or bolded. With decimal numbers, there are two scenarios that apply only to rational numbers. So they need to have a finite number of decimals, and finite, we'll talk about that a little bit later as well, but finite means there is a fixed number, or there is an end to how many there are. Right, so there is a set number of decimal places, or it ends, right? So the decimals end, so like 0.75, that ends. Or it's a repeating decimal, And what I mean by repeating decimal is that it's the same value or same set of values over and over and over again. So for example, if you were to take 1/3 and divide that or turn it into a decimal, that's the same as 0.33333. And the 3 is basically repeating. Right? So that's an example of a repeating decimal. Finite, and so those are the two scenarios when we're looking at decimal places for our rational numbers. Other than that, if it's a fraction, it's a rational number. For example, we might see something like 0.75 or even like 0.125. Right? Those are rational numbers. Those are finite number. There's a finite number of decimal places, and then we have the repeating decimal examples. So you might say like a tape measure. So this one's more specific, right? You might be looking at fractions, or when you're looking at inches, you look at half values and so on. If you're weighing something on a scale, technically you go into half values and decimals. Measuring things like in cups, so 1/2 a cup, 1 cup, 3/4 of a cup, and so on. Those are examples of some rational values. And finally, the other one, this one doesn't encapsulate or isn't a shell. This is separate from all of the other values we looked at. So previously, like I said, going back over them, your natural or counting numbers, then you go your whole numbers, then your integers, and then your rational numbers. Those are all in kind of the same shell, with rational numbers including all of them. Irrational numbers is separate from that. And they're separate because they have decimals that do not terminate or have a repeating number at the end. Right? So basically, this is the opposite of the decimal scenarios that we may come up with for rational numbers. So if they don't terminate or end, or they don't have that repeating value at the end, they're considered irrational numbers. And some popular or common examples might be pi, right? 3.14 is what we know it as, generally speaking, but there's a lot more to that. 3.14, 159, 265, 35, and so on and so on. And it doesn't end. Mathematicians haven't found the end to that number, right? They're still calculating numbers of pi. This E, we can start to see the number here. This is what's called Euler's number. So that is, again, a never ending, or it doesn't terminate at the end, so it keeps on going. And if you take the square root of non-square numbers, right? So numbers that take the square root of non-perfect squares, right? So things that don't have a perfect square. So for example, if I were to take the square root of, say, 4, I get 2. Square root of 1 is 1, right? Those are perfect squares. They give me nice numbers. But if I was to take the square root of, say, 2, 3, 5, oops, I wrote 3 again, 5, and so on, what would we get? If you were to plug that into your calculator, square root 2, right, you're going to get a long number. And it probably doesn't end. It might end in your calculator because it is only going to show so many values, but that doesn't mean that it actually ends. Right? So if you look at some of these, what we call radicals or roots, those are also other examples of irrational numbers. So those are all the different types of number sets that we're going to look at. So you are going to be required to just kind of familiarize yourself with those. If you're given a set of values or certain values, can you place them or can you categorize them into certain subsets? But finally, like we said, real numbers, this is what everything that you've looked at. So all of those subsets that we just talked about, they all are considered real numbers. So all the rational and all the irrational numbers are considered real numbers. Basically, any value you can think of, it's a real number. And there's an infinite number of real numbers. And this R is just kind of what we use mathematically to represent any real number, or the set of any real number. So let's just look at one or two examples just to kind of work through this, or just to, again, talk about some of these concepts. So for example, we see two different number lines. We see a whole numbers number line, 1, 0, 1, 2, 3, 4, and so on, only positive values. And we see a rational numbers number line, right? We see the half values and so on. We see or values that end in a repeating value. We see positive, we see negative, we see 0. Now, is each set finite or infinite? And if you're not too sure what those two words mean, we did kind of talk about them already, but just jumping ahead, finite means having an end. Oops, I kind of misspelled there. So finite means having an end. It stops at some point. Infinite means having no end. It goes on forever. So going back up to our number line, even though we see certain values, again, the arrows indicate that it continues. So these pattern continues, or we go on to 11 and 12 and so on. So is the whole number set finite or infinite? Is the rational numbers set finite or infinite? Well, in this case, they're both infinite. Right? They both go on forever. They both don't have an end. Now, whole numbers, they go on forever in the positive direction. They can't go past 0 because then we move into integers, but it's still an infinite number of values in the positive end. Rational numbers, it's the same thing. It goes on in the positive direction forever, for infinitely, as well as the negative end infinitely as well. So even though whole numbers does have a lower limit, you might say, both sets are still considered infinite. And then lastly, is each set dense? So what do we mean by dense? Well, again, let's just jump ahead quickly. Dense means a number set is dense if you can always find another number between any two numbers. So can we find a number between any two numbers? Well, let's go and look. So the number line will help us, right? If I have 2 and 9 highlighted, can I find numbers between them? Yep, I see 3, 4, 5, 6, 7, 8. So let's pick 2 more. And just for sake of argument, to speed it up, I'm going to pick 5 and 6. Is there any number between 5 and 6? No. So there are numbers between 5 and 6, but are there whole numbers between 5 and 6? In this case, no, there is not. There are not whole numbers between 5 and 6. So that means that the whole numbers subset is not dense. So whole numbers are not dense. Well, what about rational numbers? Right, I can see a bunch of values. Let's just pick 2 easy ones. We'll go 0 and 2/3. Is there a rational number between 0 and 2/3? Is there a rational number between 0 and 2/3? Is there a fraction between them? Sure. 1/3. Right? Is there a fraction between 0 and 1/3? Yep. We can find a smaller fraction, right? 1/4, 1/5, 1/8, 1/9, 1/10, 1/12, 1/13, 1/100th is between 0 and 1/3. Right? So we can keep getting smaller and smaller with our fractions. So that means that rational numbers are dense. So rational numbers are dense. So again, just more ways to describe some of our number set. Whole numbers are not dense by definition. Rational numbers are dense by definition. And again, that's the end of the lesson. So again, the main things are just understanding the different subsets or different categories of numbers that we might come across as well as some ways to describe them in terms of if they're finite or infinite, and whether they're dense or not dense.